We have uncovered a disturbing reality. Our relentless perception is inadequate with regards to grasping the peril of the universe in its early phases. The hypothesis of the universe's beginning reaches its limits. This drives us to consider new theories about its initial fragment. The question arises, how did the universe take shape and form, and why? This new discovery challenges even the most experienced astronomers to learn more about the Big Bang and the ever-evolving nuances of the revelation. We must examine the risks of the Big Bang itself. Contrary to popular belief, the Big Bang was not an explosion in pre-existing space. Rather, it was space itself that began around 13.8 billion years ago, along with time and matter. An extraordinary aspect of physics and cosmology is the singularity, where gravity becomes so powerful that the curvature of spacetime becomes infinite. Nowadays, following billions of years since the universe's birth, we see that the cosmos is part of a vast, collaborative evolution. For scientists, this represents a crucial piece of understanding the universe's life and its continuous expansion. The universe is not expanding into pre-existing space. Rather, space itself is continually growing. According to classical theories, the first stars began to shine between 200 and 300 million years after the Big Bang, marking the end of the so-called Dark Age. This was the time when the first luminous objects clustered together to form mature structures. However, how quickly these galaxies developed remains a persistent mystery. A significant breakthrough emerged through the first images captured by the James Webb Space Telescope in July 2022. Experts revealed that the telescope had observed galaxies that existed around 300 million years after the formation of the universe. However, compared to the galactic structures that formed billions of years later, these early systems were notably smaller and less massive. This aligns with the scientific model, which predicted that the density of matter in the early universe was insufficient to create galaxies as large as those seen today. This discovery began with the identification of 6 highly redshifted, remarkable objects by James Webb, leading to one of the most significant cosmological crises of recent times. Despite being comparable in age to the galaxies documented today, these newfound structures were nearly as massive as our own Milky Way galaxy. This has created a fascinating mystery in Big Bang cosmology. After analyzing data obtained by the near-infrared camera, astronomers identified these distant light sources. Using redshift data, experts confirmed that the light from these objects took more than 13 billion years to reach Earth. Thus, these structures had already formed between 570 and 700 million years after the Big Bang. Upon studying these objects, it was concluded that the James Webb Telescope had captured 6 early cosmic structures that were extraordinarily large. These findings challenged traditional cosmology. Instead of identifying the expected dwarf galaxies, the telescope observed structures nearly as massive as the Milky Way. This implies that the density of matter in the early universe must have been several times greater than previously assumed. Alternatively, these galaxies may have formed in ways entirely unknown to us. These revelations have reignited debates surrounding the Big Bang theory, encouraging further evaluation. Many astronomers with alternative perspectives have voiced frustration, often dismissed as radical or incorrect. Yet, even scientists who support the Big Bang model face unanswered questions. For instance, how and why did something arise from nothing 13.8 billion years ago? Could something truly originate from nothing, or was there a triggering event, or mere chance? Stephen Hawking suggested that time, as we understand it, began with the Big Bang, making it impossible for the process to have been initiated by an external cause. A similar question concerns the uniformity of radiation and matter density throughout the universe. Regardless of the direction or distance observed, large-scale structures and cosmic radiation show remarkable consistency. Current physicists explain this phenomenon through the theory of cosmic inflation, which suggests that the universe underwent an incredibly rapid expansion shortly after the Big Bang. However, some experts propose further theories, including the concept of turbulent growth. According to this idea, growth produced specific regions, like bubbles, while remaining uneven elsewhere. This raises the possibility that different universes might have formed within these bubbles, each with its own physical laws. This leads to an inevitable question. What if the universe does not represent the entirety of existence? Could another universe have existed before ours? If so, the Big Bang might be part of a larger cycle. From this perspective, our universe could belong to a more complex system involving perpetual cycles of collapse and rebirth. Alternative theories also suggest that the universe may have existed eternally, negating the need for a Big Bang. In 1955, for instance, NASA published an article proposing that the universe may have always existed, with no expansion, its evolution giving only the illusion of growth. Another fascinating, albeit controversial, theory comes from quantum physics and string theory. Some experiments propose that our universe might be a projection or a higher-dimensional simulation. While this may sound like science fiction, it ties into the Kardashev scale, which measures a civilization's ability to harness energy. A Type 3 civilization, capable of harnessing the energy of an entire galaxy, might create such a simulation. However, determining the validity of this idea remains a complex endeavor. Exploring the depths of cosmology and the universe's origins leads to profound mysteries and ongoing scientific inquiry. The James Webb Space Telescope's recent images have reignited debates about the fabric of reality, challenging established theories and prompting scientists to reconsider fundamental aspects of cosmological knowledge. At the core of this inquiry lies the concept of the universe's foundation. According to prevailing theories, the universe emerged from a hot, dense state approximately 13.8 billion years ago, expanding rapidly and giving rise to space-time and matter as we know it. This event marked not just an explosion within pre-existing space, but the very beginning of space itself. The discovery of early structures by the James Webb Telescope challenges assumptions about how quickly the universe's structure formed. These galaxies, identified within a few hundred million years of the Big Bang, appear remarkably advanced and massive compared to current models. One key question arising from these findings is the nature of cosmic inflation. Traditional theories suggest inflation occurred fractions of a second after the Big Bang, explaining the uniformity of the cosmic microwave background radiation observed today. However, the observed complexity of early galaxies suggests new complexities in the universe's formation that may require modifications to inflationary models. The James Webb Space Telescope's discoveries have also reignited debates about the multiverse hypothesis. If our universe is one of many, each governed by its own unique set of physical laws, the early appearance of massive galaxies might not be as surprising. Perhaps these structures are the product of conditions unique to our universe, or they may reflect interactions with other universes in a multiversal framework. Another area of exploration is the role of primordial black holes in the early universe. These hypothetical black holes, formed shortly after the Big Bang, could have acted as seeds for galaxy formation, providing the gravitational pull necessary to gather matter and form large structures. If primordial black holes exist, they might also explain some of the anomalies observed in the early universe. The implications of these discoveries extend beyond cosmology. They touch on fundamental philosophical questions about existence, time, and reality. If our universe is part of a larger multiversal system or a simulation, what does that mean for our understanding of life, consciousness, and the nature of existence itself? These are questions that bridge the gap between science and philosophy, challenging us to think about the universe in new and profound ways. As scientists continue to analyze the data from the James Webb Space Telescope, they are also preparing for future missions that could shed more light on these mysteries. Upcoming projects like the Nancy Grace Roman Space Telescope and the next generation of ground-based observatories will provide even more detailed views of the universe, potentially uncovering new clues about its origins and evolution. In the meantime, the discoveries already made have sparked a renaissance in cosmology, inspiring new theories and collaborations across disciplines. The early universe remains one of the most enigmatic and awe-inspiring subjects in science, and each new piece of evidence brings us closer to understanding our cosmic roots. Ultimately, the universe's story is still being written, and our place within it continues to evolve. Whether through the lens of a telescope, the equations of theoretical physics, or the boundless imagination of human inquiry, the quest to unravel the universe's mysteries is a journey without end, one that will forever challenge and inspire us. The question of the universe's ultimate fate is another significant puzzle in cosmology, intricately tied to these recent discoveries. Will the universe continue expanding indefinitely, driven by dark energy, until galaxies drift so far apart that stars fade into darkness, a scenario known as the heat death? Or could gravitational forces eventually overcome this expansion, leading to a big crunch, where everything collapses back into a singularity? Some theorists propose a more cyclic model, where the universe undergoes repeated phases of expansion and contraction, a big bounce. If these newly observed structures formed during the universe's early stages challenge our understanding of its density and expansion, they may also have implications for its long-term trajectory. In parallel, the role of quantum mechanics in shaping the universe remains an area of intense exploration. Theories such as quantum gravity and string theory attempt to unify the seemingly incompatible principles of general relativity and quantum mechanics. These theories could hold the key to understanding the universe's origin, particularly the singularity that supposedly birthed spacetime. The concept of quantum fluctuations, tiny energy variations in the quantum vacuum, may provide clues to the initial conditions of the universe. Some physicists speculate that the Big Bang itself was a quantum event, arising from fluctuations in a pre-existing quantum field. This raises the possibility that universes could emerge spontaneously, suggesting that our universe might not be unique, but rather one of countless others arising from a vast quantum multiverse. Another provocative idea stems from the holographic principle, which suggests that the universe we perceive as three-dimensional might actually be encoded on a two-dimensional surface. This theory, rooted in string theory and black hole physics, proposes that the entire universe is akin to a hologram, with all information about the cosmos stored on a distant boundary. If true, this could revolutionize our understanding of space, time, and reality itself. In addition to these theoretical advances, observations of the universe's large-scale structure continue to offer insights. The cosmic web, a vast network of galaxies, filaments, and voids, traces the distribution of matter and energy throughout the cosmos. Studying the formation and evolution of this web, particularly in light of the new data from the James Webb Space Telescope, could help refine our models of cosmic evolution. One of the most intriguing aspects of these studies is the interplay between dark matter and baryonic matter, the ordinary matter that forms stars, planets, and living beings. Dark matter, though invisible and undetectable by traditional means, is believed to have played a crucial role in the formation of galaxies and clusters. The unexpected massiveness of the early galaxies observed by the Webb telescope suggests that dark matter's properties or distribution may differ from current predictions. As we delve deeper into these mysteries, new technologies and methodologies will be crucial. Future telescopes, such as the Square Kilometre Array, SKA, will offer unprecedented sensitivity to radio waves, allowing scientists to map the universe's structure in even greater detail. Advances in particle physics, such as experiments at the Large Hadron Collider and proposed next-generation accelerators, may provide insights into the nature of dark matter and other fundamental particles. Despite the progress being made, each discovery seems to raise more questions than it answers. This is the beauty and challenge of cosmology. It is a science of the unknown, where every breakthrough opens new doors to the unexplored. The journey to understand the universe is not just about uncovering facts, but about redefining our place within an ever-expanding cosmic story. As we gaze further into the depths of space and time, we may eventually uncover answers to some of the most profound questions humanity has ever asked. What is the true nature of the universe? How did it begin? Why does it exist at all? These questions, while rooted in science, touch on the philosophical and spiritual, challenging us to think beyond the limits of our current understanding. In the end, the universe's greatest secrets may remain forever out of reach. Yet, the pursuit of these answers is a testament to human curiosity and ingenuity. Through the lens of our telescopes and the power of our minds, we continue to explore the infinite, driven by the hope that each new discovery brings us one step closer to comprehending the cosmos' ultimate mysteries.